Lecture, we talked about decomposition in general, the motivations for decomposition, and we also talked that decomposition can be done both for linear problems and nonlinear problems. This lecture we are going to focus on Dantzig-Wolfe decomposition, which is a technique for solving linear problems in a distributed way. All right, let's get started with our original problem. So the original problem was minimizing Cx subject to Ex is equal to F and Ax is equal to B. All x's are upper bound. So we had two sets of constraints, non-coupling and coupling constraints. And then we mentioned that we want to decompose this into R subproblems. So as you can see, the objective function has been decomposed into R subproblems. Each of them are assigned a set of variables. So we have variable x1 for subproblem 1, x2 for subproblem 2, and xr for subproblem r. And each of these are a vector of variables. We also mentioned that each subproblem has been assigned a set of non-coupling constraints, which means that constraint only refer to this specific subproblem. And so on. For the last one, we have ER XR is equal to FR. Now we are going to see how we can solve this using linear decomposition algorithm. All right, so here is the general idea. So we start with defining each of the subproblems very clearly. So if you look at here, the objective function for each subproblem is the coefficients for that specific subproblem multiplied by the set of variables for that subproblem. For example, for subproblem 1, this is just example. What we have is minimizing C1 transpose X1 subject to the non-coupling constraint for that specific subproblem, which is E1 X1 is equal to F1, and for the set of variables of that specific subproblem, we want to upper bound these variables. All right. So as you can see, the complicating constraint is evaluated separately, and we assume that there are n number of complicating or coupling constraints. So how does the decomposition technique works? First, we solve the problem for different CKs or for different subproblems. So for each of the subproblems, we try to find a set of feasible solutions. So you just choose any arbitrary values for the coefficients. You just want to make sure that the solutions, let's say the first solution set, satisfies all of the constraints for each of the subproblems. For example, if one of our subproblems is minimizing 2x1 plus x2 subject to x1 plus x2 is equal to 4, and x1, x2 are all positive, less than or equal to 6. A feasible solution to this is x1 is equal to x2 is equal to 2. So When we talk about feasible solution, we don't look at the objective function. We only want to satisfy the constraints. In this example, x1 plus x2 is equal to 4. So if I choose x1 equal to 2, x2 equal to 2, sum of them is going to be 4, which satisfies this constraint. Also, x1 and x2 satisfy the second constraint, which is they should be between 0 and 6. So we find sets of feasible solutions for each of the subproblems. That's the very first step in decomposition. Let me erase this part. All right. So now assume that you already found these sets of feasible solution set 1, set 2. So we found P sets of feasible solutions. In the next step, what we are going to do, we are going to use any combination of these solutions to generate a new feasible solution. Because we are dealing with linear programming, linear optimization problem, so if you use a convex combination, which means you have a set of coefficients that their summation is equal to 1 of the existing generated solutions, then the new solution is going to be feasible as well. Then we use a step-by-step procedure to add feasible solutions and find optimal values of these coefficient use that helps you to fulfill the complicating constraint. So why do we do that? Because as you can see here, we only consider the subproblems to generate this feasible solution, which means we still haven't considered the complicating constraint. But during these updates, that's where we are going to take into account the complicating constraint for our update and for making sure that we are moving towards the optimal solution. All right. So this is the overview of Dantzig-Wolfe decomposition. We have the master problem and we have subproblems. Again, just to emphasize, each subproblem only has the variables corresponding to that subproblem and the non-complicating constraints corresponding to that subproblem, and also the positivity and boundaries of the variables. This is for each of the subproblems. Then after, so step 0, initializing. Find initial solutions to relaxed problems. So this is the step where you find feasible solutions for each of the subproblems. Step 1 is master problem solution. So after finding these feasible solutions, we are going to formulate the master problem and make sure that the master problem fulfills the coupling constraint. Step 2, again, we go to the relaxed problem solution. Generate solution of the relaxed problem to improve the current solution. That's the iterative approach to improve our variables until we converge to the optimal solution. In step 3, you check whether you have converged to the optimal solution or not. We call it convergence checking. And finally, in step 4, we calculate the optimal values for all of the variables after we ensure that we reach the optimality. If not, actually, after step 3, we are going to repeat these steps. So after we have a new solution, if it didn't converge, if it converges, we calculate the optimal values. If not, we go to step 1 and update the master problem, find a new solution, and keep going until we converge or we meet the convergence criteria. Right. So again, here's the first step. we have this problem, we have our subproblems, we have complicating constraints, we have non-complicating constraints, and we have the constraints for our variables to be positive. Step 0, initialization. So we solve all of the subproblems with different objective functions. So, and we generate P feasible solutions. So finding feasible solutions for all subproblems. Again, I want to emphasize just one example. Let's say one of your subproblems looks like this: x1 plus x2 plus 3x3 subject to x1 plus 2x2 is equal to 10, x2 plus x3 is equal to 8, x1, x2, x3 less than or equal to 2x. So in this case, if I want to find a feasible solution, one feasible solution could be x1 is equal to 0, x2 is equal to 5, and x3 is equal to 3. So why this is feasible? Because it's when we find x1 plus 2x2, x1 is going to be 10, and when we find x2 plus x3, it's going to be 8. All right, so this is one feasible solution. Another feasible solution could be x1 is equal to 2, x2 is equal to 4, and x3 is equal to 4. So 2, 4, 4. Why that's the case? Because x1 plus 2x2 is equal to 10, and x2 plus x3 is equal to 8. So what we did here, we generated two feasible solutions, 1 and 2. All right. So this is step 0. We call it initialization. Step 1 is the master problem solution. So what we are going to do, we are going to find the value of complicating constraint I for solution S. So let's say you have a number of complicating constraints. So our complicating constraints could be sigma coefficient A multiplied by Aij xi is equal to, let's say, fi. So when we say value of complicating constraint I, which means we want to evaluate this at the current solution. And we call that R sub I S. So this is for solution S. So S can be any value from 1 to P, which P is number of generated feasible solutions. All right. Then we have to evaluate the value of the overall objective function at solution S. What's the overall objective function? It's sigma ck transpose xk for all of the k from 1 to r. So we want to find the value of the original objective function at each of the generated solutions. So now you have these two numbers for all of the generated solutions. What you are going to do, we are going to formulate the master problem. So the objective function for master problem is using these values. We already know these values. And the variables for this are the coefficients. What are these coefficients? These are the same coefficients that we mentioned here. So these are the same coefficients that we use here to update our solution in each iteration. So in order to find this, we have to solve the master problem. All right. back again to master problem. So the goal of master problem, the goal to find coefficients UI for generating a new feasible solution. But this is not any random feasible solution, right? This is a feasible solution which is aligned with moving towards the optimal value of the objective function. I'm going to share a link to the book by Dantzig and Wolfe that explain all of the theories behind why this is working, because it has a lot of theories behind this. This is it has all proven theorems that shows why this is converging to the optimal solution. And then we have, so this is our objective function. And why do we have P here? P is number of generated feasible solutions, right? All right. We also have a constraint here. We have an inequality constraint. So our i's are the values that we have from the complicating constraint. U's again are our unknown coefficients, and bi's are the right-hand side values from the original problem. So we assign, these are the Lagrange multipliers mentioned here. If you remember, when we wanted to solve optimization problem, we assign Lagrange multipliers to each constraint, and this is the Lagrange multiplier for the second constraint. So the second constraint says sum of all of these coefficients should be equal to 1. Again, this constraint, we discussed about this before. So here, we already talked about this constraint. So the master problem ensures two things. First, sigma, or sum of all of these coefficients, is equal to 1. And second, it helps us to find the coefficients to move toward the optimal solution. All right. Now let's say and we want all of these coefficients to be positive. Now let's say we have all of these coefficients, U1, UP, and we already have sets of feasible solutions, X1, set 1 and XP. Now let's see what's the next step. In the next step, we solve the relaxed problems by updating the objective function. But how do we update the objective function? Let's go back one more time. Here, we had vector mu, which shows the Lagrange multipliers for this constraint. We are going to use this vector as well as the coefficient for coupling constraint to update the objective function of each of our subproblems. We call this a relaxed subproblem. So if you remember, originally our subproblems were like this: CK transpose XK subject to EK XK is equal to FK, and XK is upper bounded by SK. All right. So how did we relax this? We added this new term. What are the components of this new term? Mu is Lagrange multipliers from our master problem, and A, coefficients of coupling constraint, right? Perfect. Now that we have this, we are going to generate new set of feasible solutions. For each of the subproblems, we first relax them, find the relaxed version, and then we generate new set of feasible solutions. All right, let's see what's next step. So in the third step, we want to check whether the convergence is reached or not. In order to do that, we are going to use the summation of all of the relaxed objective functions. So this is the relaxed objective function of subproblem K. So we find the value of this at each of the generated solutions, at the latest generated solution, which is xk, additional xk, and we sum it up with the coefficients, the Lagrange multiplier for the equality constraint of master problem. So this is Lagrange multiplier for the equality constraint in master problem. Please note that in master problem, we only have one equality constraint. Let's go back to the master problem. So in master problem, we only have one equality constraint, which is sum of all variables should be equal to 1. All right. So if this convergence criteria is holding, which means this value is positive, then we have reached the optimal solution. So we should go to the next step. If not, the relaxed problem of the current solution can be used to improve the solution of the master problem. So we go to step 1. So we have a new feasible solution, and then we go to step 1 to repeat the same steps. All right. So let's say we have reached the convergence. What's next? So we already have the optimal values of U1, U2, and UP, right? So what we have to do, our optimal solution for subproblem K is sum of all of the generated solutions using these coefficients U's from 1 to P. This is going to be our optimal solution for subproblem K, where K is from 1 to R. Because originally we decomposed our original problem into R subproblems. All right, let's take a look at this again. We had the master problem, we had subproblems. Each of the subproblems solve their own problem to generate a set of feasible solutions. So let's say 1, 2, R. So this one sends back x1, x2, x3. After they send back their answers, what the master problem does is going to solve the master problem and send these mu values to them. What were the mu values? Mu values are the Lagrange multipliers. Actually, it's vector. Vector of Lagrange multipliers corresponding to inequality constraints of our master problem. And after we send back these values, what we are going to do, we are going to solve each of the relaxed subproblems. So relaxed subproblems, how do we do that? We update the coefficient, let's say C1 transpose plus mu multiplied by A. So we update the coefficients for each of the subproblems, we solve them again, and this iteration goes on and on until we reach convergence. After we reach convergence, we have the optimal values of U1 PUP or the coefficients. Based on this, we say U1 multiplied by X1 plus U2 multiplied by X2. X1 means the first set of feasible solutions, and so on to find the optimal values for variables. So this was all for Dantzig-Wolfe decomposition. I'm going to provide some additional links to the book by Dantzig and Wolfe. So if you're interested in the theories behind this algorithm and why it's working and it's converging to the optimal solution, you can go through that book.